Long story short, yeah.
Long story short,
Wait, what is Monday, class or lab?
No, Monday's class.
Well, Monday's going to be a mix.
Yeah, I thought we had that demonstration thing left or whatever.
Okay. So molecular mass spectrometry, right? It's a detector. That's what it is. Right? It doesn't separate stuff. It's just simply a detector. And you have to have something up front of this detector, right? That's going to separate all your mixture into pure components. Okay? And then, depending on how the mass spec is, the type of mass spec, all right, is the rest of it. And, however, this, regardless of the innards, the guts of a mass spec, whether it's ion trap or quadrupole like this one pictured, it has a capability that other detectors don't have. What is that? It's a pretty nice capability. Haul it into the jungle, find out why these people are getting their headaches cured, right? What I'm looking at is compounds. It can actually do a library search, right? You can, and just, it's really nice. Some dude's walking around all right? You take some of his blood, probably have to do solid phase microextraction on it because you can't shoot blood in the GC. You find out all the organic components in his blood, right? The ones that don't decompose on you in the inlet, and find out what's going on. Okay. Some general concepts behind mass spec. What is a mass spectrum? Okay, now, if you've had analytical, hopefully you remember this. What is a mass spectrum? What does it look like? Yeah, pretty much that's what it's going to look like, right? Mass of a whole bunch of ions, right? And maybe there's one big peak, but there's a whole bunch of ions. So that means this has to be mass down here. It's mass to charge, but charge is always positive 1, so it's kind of redundant. But yeah, because what it is well, remember with this mass, it has, what's this axis? What is this axis? Mass is down here.
So we're saying that the one on the far right is bigger than the one.
Yeah, this one's more massive than that one. So it's just intensity. It's just intensity.
It's always intensity.
But okay, that's what it is, but yeah, there's a better, I think, a more analogous term for this. Every molecule, right? Are all molecules of the same compound identical? What would make them different? Are all molecules of the same compound the same? They wouldn't be. They wouldn't be the same compound, right? Yeah, water. Take water. Take cocaine. Take whatever you want to put in the GC. Its molecules are all identical, right? So that means that there's a mass spectrum that corresponds to that cocaine molecule, that ethanol molecule, that whatever molecule. There's a mass spectrum that corresponds to it. A mass spectrum is actually a chemical fingerprint. That's the best way, I think, to describe a mass spectrum. What is it? Chemical fingerprint. I mean, because when you think of fingerprint, you think identity, everything, okay? Obtaining a mass spectrum starts with ionization. Okay, there's a whole bunch in this table. Where is ours? Okay, here's a hint. It's this kind. Oh, there, it says it right here. Electron impact. Okay. The book gives this equation for ionization. This is the first step. So this is what's your analyte here. Where's your analyte? It's represented by what? Big M. Probably for molecule. Yeah. So it's not ionized. It's your pure analyte molecule, whatever it is. And the electron, okay, that's coming from, you can go back up to that little flow diagram there. Right? Has to get slammed by an electron. Where's the electron coming from? One of these little guys. It's called a filament. And if you look at it really close, I don't know if I can't even see it. My eyes aren't good enough. But there's a little tiny wire there. Yeah, you have to stare at it. You might see it. And that's what burns out, and then you got to tear it all apart to fix it. But okay, that's where the electrons are coming off of. Anyway, where are we here? Okay. How about for you organickers? What's that little dot? When you have a dot, a radical. Okay, is this something that's really stable or something that's the exact opposite? Yeah, really unstable. Okay, so pretty much that's what it generates. Okay, did the mass of this thing change? Did its mass change? Well, technically it lost an electron, right? But you can't detect that mass change. So the best answer would be to say no, the mass didn't change of that molecule, because you can't detect the mass of an electron. Okay. You have to infer it from doing some other experiments. So they know what the mass of an electron is. It's just that these detectors aren't near sensitive enough to get that mass. What's more massive, a proton or an electron? By what factor? 10,000. 10,000. So one proton is 10,000 times more massive than an electron. We can't detect our detector, mass spectral detectors don't detect that difference in mass. But so technically it's just the same thing. During electron impact ionization, it appears it's most common to form, yeah. Electron impact ionization occurs once in, it's a million. So you have a gazooks amount of analyte coming from the column, right? That's eluting. So it doesn't take much, right? But it's, so therefore this type of ionization, it's not what? Is it or it's not? It's not. Right? Okay. But it works, right? It's like the AA, most everything goes down the drain. But it still works. Okay, some terminology. Daughter ions. All right. Yeah, the fragments, the little pieces, right? This radical just falls apart, just simply decomposes. But the point is that it decomposes into the exact same ions with the exact same intensity, the exact same fingerprint every single time. Okay, so that's why this works. And some terminology. Why would they call 91 the base peak in that picture? It's the highest one. Yeah, so they call it the base peak. Yeah. 106 is called the molecular ion peak. All right? That's the whole compound. Exactly, that's the whole compound. It's just that it's a radical and it's an ion, but its mass is the whole compound. Okay. Why do folks look for that molecular ion peak? Now, you guys picture yourself as doing some research project out in the jungle, right? And that molecular ion peak would be really useful. Because odds are whatever's curing these people's sore throats is a brand new compound. It's not going to pop up in any library search. So why would it be really useful to get that molecular ion peak? It's one little clue, right? Because then you know the entire molar mass of this thing. Yeah, it'd be one thing to help you figure it out. Okay. Well, it is really the same thing as intensity, but what they're probably doing is notice how the top is 100. And what's exactly at 100? The what peak? Base peak. So in this plot, they just plot, instead of intensity, they divided all these little intensities by this guy's height, right? And then times 100. So he's 100% because he's the base peak. So all these are just relatively abundant to that one. I think intensity is just easier to remember. Okay. And I think the concept is nice because it's really kind of preparing it for the library search. Because no matter what mass spec you shoot this compound on, the relative abundances are going to be the same. But the absolute intensities could be different because somebody's detector could be a lot newer, more efficient, more sample could be more concentrated, right? Those intensities are going to be all over the place. But the relative abundance fingerprint, right? Same for everybody's. So that's a good question. I should have that in there somewhere. Okay. Oh, we didn't answer this one. Molecular ion peak is right here. Well, if that's the molar mass of our compound, how is it possible? Oh, that's got to be an impurity, right? What the heck? It can't be an impurity. Remember, if whatever's in front of this detector did its job, that's pure analyte coming into this detector. There's no impurities here, so you can't say impurity. Mm-mm. No. Because what's going on here is when we start, well, you can kind of go up to the front or the very end of this. In that flow diagram, what's going on? There's no time for anything like that to really happen. And it's so dilute that there's nothing else there. Because if there was stuff there to be interacting with this, you couldn't get this nice clean fingerprint. So there's a lot of things that have to go right for you to get this fingerprint, right? Especially in that whole chromatograph part. Yeah, you need pure compound coming out of there. It can't be decomposed on you, nothing. Because you're going to get a mass spectrum of whatever's coming out of the column. So what is this? We lied. I lied. Are all molecules of cocaine created equally? What's different? What is different? No. What's different? No. You're close. It's an I word. Isotope. What's an isotope? What's an isotope? Different number of neutrons. Right. So pick your villain. Carbon. Right? Oxygen, nitrogen, phosphorus. They all have isotopes that occur naturally. Some molecules are simply going to be heavier than others. You can't stop it. Right? That's how you get the molar mass of carbon, right? You have to add up all the isotopes and all that fun stuff.
Some of those carbons have more neutrons, that's why.
Yeah, so that's really what's going on here. So you have carbon-13, right? Because there isn't any chlorine in here to mess it up. Chlorine isotopes. So chlorine and carbon have appreciable isotopes. So that's especially chlorine and carbon. You're gonna see these little guys, right? Look at the base peak. He's got another base. That's the same. It's the same structure, except it's got some carbon-13 in there. Or a carbon 13, not some. And that's one. Right? Because it's just 1 over. Okay. Isotopes. So there are some disadvantages. Remember we said that this is what folks want. If you're doing a big research project out, like I said, out in the middle of a prairie or something, you're after those ion peaks because your library search isn't going to do you any good. So electron impact ionization may not be the way to go. You might want a different way to ionize. And there's different types of mass spectrometers. But we're just focusing on electron impacts. That's what we use, and it's the most common too. Molecular weight must be less than 1,000. Why would that be? For this whole thing to work, physically, that compound has to travel about this far. That molecule has to travel about this far. That means it has to be in what phase? It has to be a gas, right? So it's pretty much that molecular weight limit story, right? For the GC, remember you couldn't, roughly, just a rough idea, you can't volatilize stuff over a certain molar mass. It's too heavy and decompose on you. Yeah, well, so this is just the detector. This guy right here, you're right. It's very, this is what's in the last 5-10 years, LC. Because just think how broad this is. Now you can shoot anything on that machine, right? And have all the power of a mass spectrometer detector. Now it's a very expensive machine, and has a it'd be a lot of maintenance. So. Good question, right? The LC, he doesn't care. You can shoot proteins on there, whatever you want. There's no molecular weight limit. But you're not going to be able to have a mass spec detector on it, right? If you want to, because it has to be a gas. It has to volatilize. Right? So, but still, it opens up a lot of different things. Okay. Okay. What is this one about? Yeah, this is, yeah. So that's kind of the same as number 2, I think. Okay, see if you can fill in. Here's a general description of our mass spec detector. See if you can fill in. See those 6 on the bottom there? These. Just put them in where you think they go. So.
Won't have voice in here. So this is not voice route. Sorry. These are the options.
Yeah, options are on the bottom down here. 6 of them. Now, when you're doing this, I would suggest keeping this guy in mind, right? Keep this in mind when you're trying to figure this out. There's a few, well, there's a lot there's answers in there, right there.
This is the answers.
I don't think so.
Yeah, no, yeah.
ionized before it goes in. Or, I don't think the inlet's like where it enters.
That's okay. That's fine. That's what you do in real life, man. You gotta look at it, Google it. That's what I would do. If you're paying $100 a month for that phone, you should make use of it. I don't know if we have this one, though. I don't. All right, let's see if we can fill this stuff in. This first box, for me personally, is what really sucks. It makes my job. Well, I guess it gives me something to do, which is job security. The problem is okay, think of it's liquid chromatograph or gas chromatograph. Something has to be separating out your analytes, right? Something has to be separating out this mixture, making it really pure. What pressure is this at? Yeah, atmospheric, right? Or if it's a liquid chromatograph, it could be like 1,000 psi. Okay, but otherwise, if it's a gas chromatograph, essentially 1 atmosphere, maybe a little bit higher, right? Because you have to push it through the column. Inside this dashed line is what pressure? Essentially no pressure. Why? Why is the pressure so low? You have to get your analyte from where to where? From here to here. A physical macroscopic distance. You have to get a gas molecule to go that far. If there's anything in there, especially this stuff, there's no bloody way it's going to get there, right? It's called mean free path, and there's a technical jargon for it. The average distance between collisions. It's got to be literally a meter long before it collides with anything. So this is a very, very low pressure. What's a torr? It's a millimeter of mercury, same thing. Okay. If you want to get into atmospheres, just divide it by 760, so it's even smaller. All right. Okay. So this is the inlet system. This is the inlet system. That's A. And this is I have to tear the whole thing apart pretty much every time we shut down and turn back on the GC. And to this day, I'm not so sure I understand how this inlet system works. Because all this is this big, long tube, and there's something funky going on in there because it's really hard to stick the column in there. So somehow it's allowing something to go from atmospheric to an extremely low pressure. Right? And that boundary is secure, it's stable, it's at equilibrium, it's not causing any problems. How it does it, anyway. That's our inlet system. And you get a lot of leaks there, and that's the problem. I have to keep that up. So the stuff is coming out of the chromatograph, and it goes through this funky engineering inlet system, and then it probably goes to where? Yeah, it has to get analyzed. All right? So good. It gets ionized. So hopefully 1 in a million is going to get ionized. Okay? If it doesn't get ionized, okay, would it keep going straight? No, because you're going to have all these metal rods and things in here, and they call them ion lenses and things. So they only work by having charged particles, because they're charged. You're controlling the magnetic field and electric fields all in this area, this meter-long area. And so if it's not charged, it can't interact. So it's just going to... What is this? The vacuum system. It'll just suck everything out of there.
You said only like 1 in a million molecules makes it through there or whatever?
1 in a
million gets ionized?
1 in a million gets ionized. Yeah.
So like a lot of it stays and doesn't go through?
Yeah, a lot just gets sucked right out of the vacuum. Yeah.
Oh, so you gave that 1 in a million.
So everything goes into the vacuum system. Okay, so then, let's see, we said mass, let's see, ion source. Doesn't make it through? Vacuum. Next would be the mass analyzer. Because you don't want to hit the, right? Because only the certain mass that you're interested in is going to hit the detector. So if this guy's mass analyzer, then you'd have detector, right? D. And the last one would be, yeah. Okay. How does it work? All right, now. All right, now if you had analyticals, please stand up. If you had analytical with me, please stand up. That's everybody, right?
Recently, or?
Yeah, let's say recently. Let's say recently. If you had it recently. Okay. So here's your tools. Now, the folks who had it recently are going to explain to you how this works. Divvy it up. All right. See how well these guys remember this stuff. So try to assign everybody a different job, like we did in class there. Now identify everybody's different job here. Let our spectators know who's doing what or what they're supposed to be doing. Now hang on. What are you? So everyone should have a name, right? For example, let me get you started. I would call Anna the what? The detector. Right? I would call her the detector. Okay. Okay. Emily's the computer readout. All right. Okay. Now, man, we've got a whole bunch of people being the quadrupole, right? We should call it the mass analyzer, right? Because then it's a general speak for all these. Okay. And what is this mass analyzer doing? What is it doing? The computer readout should be telling us. It's controlling it. Because the detector, all the detector does is just say, ding, I detected something. Right? That's all it does. What are you telling this quad to do?
Let certain stuff through.
Yes, it's picking out certain masses, but how? How are you going to tell them to do it? They're going to apply what? Different, combinations of voltages and magnetic fields in here. Pretty much just voltage is what it's playing around with, right? So that only a particular mass can get through, right? And it has to have a charge, otherwise the whole thing's not going to interact. So it only applies a certain energy for something to get through. Okay, so that's what Emily's doing. Now what's going on over here? Okay, but you have a mixture going on right here. So what are you going to be? No. What piece of equipment are you going to be?
Oh, the inlet.
Okay, she's the inlet. So you're going to inject everything into her. Now, when you say inlet, are you talking about the GC or the inlet system?
Inlet system.
Okay. Would this be shooting through the inlet system? No. It's not separated. Right? So this is what would shoot through the GC inlet or the LC inlet, right? Okay, so but she wants to be the inlet system, so she better just take what out of here? Yeah, just pick a pure thing here. Okay? Now what are you going to be? Now what's left? What's left? Think of the components that are left. She's the inlet system.
Am I the sample?
Well, she's essentially got the sample in her hand. The ion source, right? So you're going to try to blast her with an electron. Now, don't hurt her, right? But you're going to miss her, right? 999,909, right out of one. So,
Oh yeah.
all right. Okay. So do we have everything covered now?
No, we need the vacuum.
Yeah.
He's the vacuum.
If don't breathe, inhale the entire time, right? All right, so let's try it.
Got stuck with the balls.
Now before we get going here, does this thing ever turn off? Yeah, that thing's on the whole time. What is this thing doing? All right, this guy. What is he set for? Emily, what is it? What are you looking for? What type of ion? What mass?
It's Agent Orange.
Are you looking for something really light or something really heavy? Okay, she set these guys to a very light mass. Fine. Okay. So now you're a molecule though. So you really are looking like this, right? This is a molecule. So this is, even though it looks like a bunch of different things, those are the daughter ions.
Yeah.
Right? Okay. So the blaster?
Doesn't she miss like a couple?
She missed. We're waiting years and years and years. She finally strikes Adriana. Okay. Now, hang on. Is it just this one that's flying out?
It's
It's all of them,
I gotta throw all of
right? Okay,
Throw
but
them at a time.
now you need some help here, right? Help her out here. Hold some of this stuff, right? Now you're the vacuum. Now you're going to be grabbing stuff. You're going to be grabbing stuff, right? But help her hold this stuff, right? Now the only what is going to make it through here?
Light.
The light. So you guys you're flying through here, right?
Can
All right.
send it through?
All right. Now only what's going to make it through?
Light.
So then
Okay, it depends on which light she's set up to, right? Whether it's this one or that one, right? So give all the other ones to the vacuum system. If it's not going to make it through there, they have to give them to the vacuum system. Okay. Now, do you remember the concept that I tried to bring across and showing how it got through there?
Bounce?
The bounce. You apply a certain energy, all right? Right? It's only that energy that makes it through, right? Because this guy is applying that energy, right? Okay. So now bring all that stuff back, right? So she got ding ding. She got a nice peak. Now this guy is scanning to probably a heavier mass, right?
No, I don't. It's too heavy. So that one gets sucked up.
Yeah.
And this golf ball is actually pretty light. I'm not sure.
Yeah, well, he's heavier. Just use him. Okay.
There you go.
Oh, he's going to be really light. He's going to
He's
hardly
light.
take any energy at all,
So
right?
does he go through then?
Well, none of these are going to bounce. But the point is, right?
He goes through.
To get this to bounce through there, you have to apply a pretty nice energy, right? And that's what this thing is applying to it. If it doesn't make it through, it just gets sucked out by, right? It's gonna take a lot of energy to get that to bounce through there. And that's the only energy it's applying. So it's applying that much energy, anything light is gonna go flying out really early. And it gets sucked out, right? Make sense? All right, so good deal. Good deal.
Good job.
I thought it was going to be like the batting cages.
What's a tick?
Annoying little thing that bites you because you
Yeah. Close. What's a tick? Draw one of each. We already drew a mass spectrum. Right? There's a mass spectrum. Right? The tick, to appreciate what's going on here, you have to realize how fast this thing is operating. This thing just analyzed from extremely low mass, maybe like 20 or 18 grams per mole, all the way up to like 250 or 300 grams per mole, molar mass, roughly, in a microsecond. So it scanned, I mean, it's crazy how fast this thing can do that. But what it's doing is, if you take, but it takes a microsecond, right? So anyway, if you time Let's make it look more like a GC, right? It looks just like a tick, looks just like a regular GC chromatogram, right? A tick does. But what is it? It's actually not these nice smooth lines. It's actually dots. But they're so close together, you can't even tell. Right? When you start doing the GCMS lab, we're going to set the parameters so you can actually see that a tick is actually connecting the dots. So when you take your little cursor, your mouse, and you click on a tick, you have to double click on it, you're actually selecting one of these dots. And each one of those dots, right, it's a signal, add up all these intensities for a particular mass spectrum obtained at that time. That's going to be your signal. That's going to be your intensity. Total ion chromatogram. There is a lot of these are huge, huge files because every single point is a mass spectrum. Every single point is a mass
So
spectrum.
when you're looking into the library, you're just looking at text, mass spectrums.
When this is the fingerprint. This is a regular chromatogram, right? Oh, here's a compound, here's a compound, here's a compound. Okay? So notice the difference. This is mass on the bottom. This one is time. Retention time, same as always. But how did it obtain it? The time is just like always, the time that it detects the signal. However, the intensity is the sum of all these intensities in that mass spectrum that it obtained at that one unit in time. And since it happens so fast, it can scan so fast, he looks nice and smooth. But if you really slow it down, you can get, you can get it to look, kind of, it's kind of still hard to see, but it looks a little more jagged if you slow it down. Okay. So that's the difference between a total ion chromatogram and a mass spectrum. Okay. Last thing. To identify an unknown analyte, a mass spectral library search may be performed. What is that? All right, somebody just shot a whole lot of every single compound known to man and just labeled them all. Got their mass spectra and labeled them all. Okay, this is what ethanol's mass spectrum looks like. Slap. Next one. Just record them all. A huge, huge data file. And you got to pay a lot of money for it. Okay, so this is what the mass spectra look like on that guy's machine, but hey, it's a fingerprint, right? So what's the problem then? Perfect match in a library search is not a guarantee. You can't go to court and say, oh, it matched the library. Well, if the lawyer doesn't know what the hell's going on. This is, I think, a big point of why science, you go into law with a science background, especially chemistry, you're going to make buku dollars. Because the whole point is argument and understanding and presenting the best argument and discussion possible. This is just one perfect example. What's the best and only way? Because library search is just that. It's what the mass spec looked like on this guy's machine at that time. You have to, if you want to show that, oh, this guy had, I don't know, LC, some drug in his system, right? You can't just compare the library search. You have to actually inject that pure compound. May verify the retention time is the same, verify that your mass spectrum is the same as his. Right? It's the same as that pure compound that you shot. That's the only way to verify an unknown. But the library search does its job, though. It tells you what to test. Man, it was ethanol, man. He was drunk. Just shoot the ethanol and verify it. Okay. Right? You have to shoot the pure ethanol. You know its retention time, its mass spectrum. Compare it with what was in the guy's blood. Match. You're done. Can't argue with it. Okay.